Tahniah. Siaran langsung ini dibawakan khas kepada anda oleh Akademi Youtuber Malaysia. Tumpukan perhatian anda. Siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Hi, Salam Sejahtera and good evening everyone. Welcome to Pusat Tuisyen Akademi Youtuber with joint venture of EDA Malaysia and Guru Malaysia. I am Mr. Peh. Currently, I am teaching at Oleh Tingkatan 6 Tun Fatimah Melaka. I am the on-duty teacher for this week. For information, Akademi Youtuber Panitia Fizik is preparing for you 2 online classes. The Form 5 class, which is for Non-DLP group, is held on every Friday, 9:30 p.m. And for this week, it's presented by Cikgu Rosemawati. And the Form 4 DLP class will be held on Sunday, like today, 8:15 p.m. And for information, the e-link schedule for today's lesson will be going to send to you at the end of the lesson, and please fill out the link with any email you are available. Without further ado, let us start our lesson today. Today I'm going to continue the subtopic of chapter 5, 5.2, damping and resonance. Okay, so in the line here, we have Jaing. Hi, Jaing. Kabar baik. Okay, so thank you for supporting me again here. Okay, so for today's lesson, you are going to learn about 2 learning standards. So let's go through the first learning standard of the day. Okay, so the first learning standard is you need to able to describe the damping and resonance for an oscillating or vibrating system. So that means that here you need to understand the meanings of damping. Then second, resonance. Okay, so let us go through the meanings or example of the oscillating and vibrating system. Okay, so here I would like to introduce to you 2 examples of oscillating system. So here we have A, we know as a simple pendulum. I think all of you is very familiar with this already. So another one, it will be B, a loaded spring. So the loaded spring will be like this. Okay, so this is the 2 examples of oscillating system. Okay, then here, an oscillating system will not continue to oscillate with the same amplitude indefinitely unless it is in a vacuum. Okay, so what is the meaning of this? So you can see from the graph. Okay, so we have 2 oscillating system. So the blue color oscillating system is conducted in A. Okay, so you can see the amplitude will be decreases. You can look at the blue color curve line. Okay, so you can see the amplitude is decreases. It'll be like this. Okay, so amplitude referring to here. Okay, so then for the black color, oscillating system is conducted in vacuum. So you can see the amplitude is not changes. Okay, so it's always the same. Okay, so these are the meanings of the sentence number 2, where oscillating system in actual condition, where conducted in A, will be decreases unless the oscillating system is conducted in the vacuum condition. Students. Okay, then the next, let us define the meanings of damping. Okay, just now I already discussed with you 2 of the graph. So when the amplitude decreases for the oscillating system were conducted in the A. Okay, so you can see for this GIF, it's very clear that this is the loaded spring. Okay, so the loaded spring amplitude decreases with time. Okay, so here this is the definition. Damping is the reduction of amplitude of an oscillating system when energy is lost as heat. Okay, so this sentence tells us already. So the damping is a process where amplitude decreases, and the amplitude decreases is due to the energy loss in terms of the heat. Okay. Okay, so here you can look at this graph. So the amplitude will gradually decrease and reach zero when oscillation stops. So this figure is quite similar to the top one. Okay, so this is the first amplitude. So initially the amplitude is higher. So that means the loaded spring is displaced at the higher displacement now, higher displacement. Okay, then the amplitude becomes smaller and smaller until zero, where the loaded spring will be stopped. Okay, okay, then so you can see in the figure, so the damping causes the amplitude and energy decreases. Okay, so the amplitude represent as A. Okay, then the A3 showing the smallest amplitude. Okay, then the next. Here, another observation you can see the T1, T2, and T3. So the T here is time taken for one oscillation. Okay, so you can see here the one oscillation referring to this, right? You learned already at 5.1. So you can see time taken for every oscillation will be the same. Okay, so this is the observation for damping in the graph of displacement against the time. Okay. Okay, so then we can also conclude that the period, besides the period, the frequency is also remain the same, because we know that the frequency relationship with period is inversely proportional, just like this formula. Okay, so when the period increases, the frequency decreases. However, both will be remain constant in damping process here. Okay, then the next. Okay, so what is the cause of the damping? So here we have two types of damping here. First, we know as the external damping. Okay, so the external damping occurs when energy is lost to overcome frictional forces or air resistance. So the damping occurs is due to the energy loss to overcome the air resistance. So another type of the damping here will be internal damping. Okay, so internal damping occurs due to energy loss caused by the compression or stretching of particle within the system. Okay, so this is the internal damping due to the compressing and stretching of the particles in system. So that means that the damping occurs is due to these two reasons: external damping and internal damping. So the external damping is due to the energy loss to overcome the friction. Then for the internal damping, there will be the energy loss caused by compression and stretching the particle in system, A1. Okay, then here, let us discuss the meanings of natural frequency, which is related to the terms of resonance, where you need to understand in your learning center 1. Okay, so just now, the learning center 1, we discussed already, you need to able to describe the damping. So just now we go through already. The damping is a process where the oscillating system cause the amplitude decreases. Okay, so caused by the internal and external damping. One, external is due to the energy loss to overcome the friction. Second, it will be the internal damping. Okay, so where energy loss is due to the compression and stretching of particles. All you want, So now we go to another terms, natural frequency. Okay, so to maintain oscillation, an external force must be applied. Okay, so just now we go through already. Okay, we go through already. So the oscillation system will be cause the amplitude decreases. So end up the oscillation system will be stopped. Okay, so to maintain the oscillation, so example, we want our pendulum continue to swing. Okay, so you have to apply external force. Okay, so a driving force is the force applied to an oscillation system to enable it to continue oscillating. So that means that the external force here referring to the driving force we want to give to the system. Okay, so here we have one example. You see, figure shows a boy pushing. Okay, actually this is a father, showing a father pushing his son each time the swing reaches the highest position. So you can see. So when reaches a high position, so the son, so the father is given the external force to the son so that the oscillation system or the swing can continue to swing here. Okay, so by doing so, the swing is able to oscillate continuously with a large amplitude. Therefore, an external force was applied to the swing. So that means that the driving force is, or the external force is actually done by the father so that the swing will continue larger amplitude. Okay, so the external force we can know as periodic external force. So these are our terms for the external force. Okay, so energy is supplied to the system by an external force. So this motion is known as force oscillation. So the force oscillation referring to the swing, is a swing where the motion continue to swing with larger amplitude caused by the periodic external force driven by his father. Okay, so thus force oscillation occur when an oscillating system is subjected to a periodic external force. So that means that the force oscillation is a motion or the swing by the sun, and the periodic external force is the driving force given by the father. Okay, then the natural frequency is a frequency at which a system oscillates freely without the influence of any external force. Okay, so these are meanings of frequency. Okay, so just now we explained already the meanings of external force is a periodic external force, where it's a driving force and cause the swing continue to swing or continues to swing with higher or large amplitude. So the swing is actually the force oscillation. Okay, so now the natural frequency tells us that the oscillation system will be continue to swing without influence by the external force here. Okay, so this will be going to discuss with the activity in your textbook where we know as the Barton's pendulum. Okay, so this will be discussed later on. Okay, so we continue to discuss the natural frequency. Okay, so here every oscillating system has its own natural frequency. So for example here, the simple pendulum is a oscillating system. Okay, so the formula where you learn at chapter 1 already. So the formula will be like this, right? F equal to 1 over 2 pi square root G over L. T will be reversed now. It's 2 pi square root of L over G. So you can see here, the F here is referring to the frequency of the system. Okay, so it's actually affected by the G and L. Okay, it's affected by G and L, I1. Okay, so here, G referring to the gravitational acceleration. Then the L will be referring to the length of the pendulum. Okay, you can see from the formula, we know that the factor affecting the natural frequency of the simple pendulum will be length and gravitational acceleration. Okay, so from the formula, we know that with the increases of the L, the frequency will be decreases. Okay. Hi. Here in the line here, we have Cikgu Hasnitah. Okay, so welcome and thank you for support, Cikgu Hasnitah. Okay, so let us continue the second relationship. Okay, so the second relationship here is when G increases, this may cause the frequency of the simple pendulum increases. Okay, so that means that the length and the G will be affecting the natural frequency of the pendulum, simple pendulum. Okay, so from the formula, you can see that the mass of the pendulum bob does not affecting the frequency and period. Okay, so this is what I want to discuss with you. Factor affecting the natural frequency of simple pendulum. Okay, then another system here is a loaded spring. Okay, so again, we discussed the factor affecting the frequency of loaded spring. Okay, so this is a formula you also go through already at chapter 1. Okay, so the formula will be F equal to 1 over 2 pi square root of K over M. For period, will be reversed now. So here you may conclude that the natural frequency of the loaded spring is depends on the K. So the K is the spring constant where you learn at chapter. Okay, so where you learn at chapter 1 or chapter 1 form 5. Okay, 1.4, you are going to learn for this now. Okay, so for form 5 student, you learn already. But if for form 4 student, you haven't learned now. Okay, so the formula will be this now. Okay, so the factor affecting the natural frequency will be the N referring to mass. Then the K will be the spring constant. Okay, so what is the spring constant? For form 5 student, I think you may know, right? For form 4 students, what is the spring constant? So spring constant is actually the indicator to show the stiffness. Okay, so the stiffness or the hardness of the spring. If the spring constant higher, that means that the spring is stiffer or harder to be compressed or stretches. Okay. Okay, so from here you can see the relationship. M increases, the F will be decreases. Okay. Okay, so when K increases, the F will be decreases. So M increases, the F will be decreases. For K increases, the F will be increases. Okay, so just now I explained to you already. So the K represent the stiffness of the spring or the hardness. So when a spring is stiff, the spring constant is high. Okay. Okay, then when a spring is soft, the spring constant will be low. Okay, so this will be affecting the frequency of the loaded spring. Okay. Can anyone can hear clearly, right? I think today's my line is not so good today, Okay, so if let's say you got face problem, cannot hear clearly, you may tell me in the chat room, okay, so that I realize and I can repeat the parts. Okay, so now we go for the meanings of resonance already. Okay, so to understand the meanings of resonance, okay, so you need to understand the natural frequency, where just now we go through already. Okay, so here, when the frequency of external force matches the natural frequency. Okay, so frequency of the external force matches the natural frequency of the system. It will oscillate with maximum amplitude. Okay, so this condition we know as resonance I1. Okay. Okay, so just now we have go through already the natural frequency of the system. For example, the spring constant. For example, the simple pendulum is affected by G and L. Then for the loaded spring, the natural frequency of the system is affected by mass of the object together with the spring constant. So that means that the natural frequency for the system will be different if they have different property. For example, the length of pendulum is different. Okay, so if the natural frequency of the system is same as the frequency given by the external force, so the system itself will be oscillate at the maximum amplitude, or without directly given the external force. Okay, so in this condition we know as resonance or I1. Okay, so during resonance, maximum energy is transferred to the system. So that's why the system will be oscillate at the maximum amplitude. If the spring achieve the condition we know as resonance. Okay, so here we are going to discuss the production of resonance by using tuning fork kits. So this is the activity in your textbook. Okay, you can refer to your textbook, and then the button pendulum also. You may see the detailed procedure at your textbook. Okay, so for resonance produced through tuning fork kits, you may refer to the page 186, activity 5.9a for the procedure. Okay, so you can see in the figure. Okay, so when two tuning fork with the same natural frequency are placed near each other, so you can just look at this figure. So they have same natural frequency. So the material, the size of tuning fork used will be the same actually now. Okay, so are placed near each other. One of the tuning fork will be strike. Okay, so you can see another tuning fork will be vibrate, right? So you can see the first tuning fork is strike. However, the second tuning fork will be vibrate together with the same natural frequency. Okay, so this occur because sound wave from the first tuning fork, which has been struck, transfer energy to the second tuning fork through the A. Okay, so this demonstrates resonance, where maximum energy is transferred when the frequency of the external force matches the natural frequency of the system. So the system referring to the second figure, a second tuning fork. Okay, then now we have another activity. You may refer to your textbook also. It's activity 5.9b at your textbook page 186 and 7 now. Okay, so this will be the arrangement. Now you can look at this figure. Okay, so in button pendulum experiment, several pendulum, you can see here A until F together with X is suspended at the same string. So this is a string. Okay. Okay, then here we need one of them set into oscillation. So that means that we need to have one of the pendulum as a driver. So the driver in this figure will be represented by XR. Okay, then each pendulum has a different length so that they have different natural frequency. This one we discussed already, right? The natural frequency for the simple pendulum is affected by the length. So the different length showing that the respective pendulum have different frequency, different natural frequency. Okay, so the pendulum that has the same length, which is the pendulum D. You see, it will be have the same length with the driver. Okay, so it will be oscillate with the largest amplitude. Or you can look at this video quick. So one of the pendulum will be swing or oscillate at the largest amplitude. Okay, so you can look at this figure now. So when the driver start to swing, okay, so all the pendulum actually will be shake and move a little. Okay, so all of the pendulum here we can know as forced oscillation because they are forced to oscillate by the driver. Okay, however, the pendulum D will be given the largest amplitude because the length of the pendulum D is same as length of the pendulum X. So that means that the natural frequency of D pendulum is same as X. Okay, so this happens because the frequency of the external oscillation force, the frequency of the external oscillation force referring to X pendulum. So it matches with the natural frequency of the pendulum D here, D here. So, and resulting in resonance for the pendulum D here. Okay. Okay, now Ivana, if you have any question, please let me know in chat room. Okay, so you may tell me you are where you come from also and your name. Okay, so you want. Okay, so next we have going to learn the second learning standard. Okay, so just now for the learning standard 1, you need to know how to describe the damping and together with resonance. So now you know already that resonance is occur due to the system with natural frequency matches with the frequency of the external force. Okay, so justify the effect of resonance in our daily life will be what you need to understand in learning standard 2. So how you apply the resonance theory you learn at learning standard 1 to your daily life. Okay, so here we're going to discuss 4 effects of the resonance in daily life. Okay, so first 2 is a back effect given by the resonance in daily life, and last 2 is actually the good effect of the resonance in our daily life. Okay, so we look at the first one. Okay, so the bridge collapsed due to the resonance. So definitely this is a back effect of the resonance. Okay, so you can see here, the Tacoma Narrow Bridge in Washington, USA collapsed on November 7, 1940, just 4 months after it opened. So this video showing the Tacoma Narrow Bridge, which collapsed due to the resonance. Okay, so why this happened? Okay, so the collapse was due to the aeroelastic resonance. So the aeroelastic resonance is a form of resonance that happens when wind forces act at a frequency matching the bridge natural frequency. So that means that the wind force frequency is the frequency of external force. and this matching the natural frequency of the bridge. So that means that the bridge will be oscillate at the highest amplitude where the resonance is occur. Okay, so although the wind speed was not unusually high, it's actually the wind is not high. Okay, it blew continuously and at a frequency close to the natural frequency of the bridge. So the problem is the frequency produced by the wind is almost the same as the natural frequency of the bridge. Okay, and because of there was no damping system or proper design to reduce this effect, so the oscillation become extreme. So that means the bridge is actually no have any special design to overcome this problem. Okay, so the bridge begin to twist violently before collapsing. Okay, so the oscillation grew stronger where you can see the amplitude or the oscillation produced by the bridge is very big. Okay, so when the wind's frequency matches the natural frequency of the bridge, so this is the resonance happens. Okay, so this event demonstrates the danger of resonance in engineering structure. Okay, so besides that, you can see another example. If a group of soldiers marches in step on the bridge, so the bridge may begin to oscillate at its natural frequency, entering a state of resonance and possibly collapsing. So that means the marching done by the soldier were producing the external force of frequency, and this matching the natural frequency of the bridge may cause the bridge oscillate at highest amplitude where the resonance happen and finally may cause collapse of the bridge. Okay, then the next bad effect of the resonance will be here. Vibrating glass or window panels. Okay, you can see when a frequency of the sound, such as from a loudspeaker or a person singing, matching the natural frequency of the glass or window panel, resonance may occur. Or you can look at this GIF. So the frequency of the sound produced by the singer is same as the natural frequency of the glass. So the glass might vibrate at the largest amplitude, okay, during the resonance condition. If too much energy is transferred, the vibration may cause the glass to crack. Okay, so this is the second effect of the resonance in our daily life. Okay, then the C is one of the good effect of the resonance in our daily application. Okay, stronger and clearer sound in musical instrument. Okay, so you can look at sentence number 1. Resonance helps amplify sound in instrument. So in musical instruments such as guitar or flutes, resonance occur when the air inside the body of the instrument vibrate at the same frequency as the string or sound produced. So again, so the frequency of the string or sound source produced by guitar string, right? Example. Okay, so cause the body of the instrument vibrate at the same frequency. Okay, so that means that the natural frequency of the body or instrument is same as the frequency produced by the sound source. Okay, so the resonance will be occur. Okay, so when the sound frequency matches the natural frequency of air cavity, maximum sound energy is transferred and the sound become louder and clearer. Okay, so here we have example of the guitar string. Okay, so for example, when a guitar string is plucked, it vibrate and produce sound. Okay, so the air inside the body of the guitar also vibrate at the same frequency, which amplified the sound through the resonance effect. Okay, so you can see at the figure, right? So the frequency produced by the string may cause the air inside the guitar vibrate at the same frequency. So the resonance will be occur and cause the louder sound produced. Okay, then we go for the last application. So this is a good effect of resonance in daily application. So resonance in radio tuner. Okay, I think all of you have experience to hear any FM station, right? So how the radio tuner cause us can accept the channel or the station we want. Okay, so this will be the one we're going to discuss here. Okay, so radio use principle of resonance to tune into a specific station. Okay, so this is a tuner of the radio. Okay, and then this is the frequency emitted by the wave from a station. Okay, so each radio station transmit electromagnetic wave at a certain frequency. So this will be going to learn at 5.7. Okay, so the radio wave will be one of the example of electromagnetic wave. So it's emitted from the radio station at certain frequency. Okay, so inside a radio, there is a tuning circuit. Okay, so this is a tuning circuit. Inside a tuning circuit, we have the inductor and capacitor. Okay, so here we're not going to discuss detail how the inductor and capacitor work. Okay, you just imagine that you tuning the radio tuner at certain frequency. For example, you want to listen the Mix FM 91.1, right? So the 91.1 megahertz where you adjust at the radio tuner may cause you to hear the radio wave where have the same frequency. Okay, so you can see here, when the frequency of the tuning circuit is adjusted to match the frequency of the desired radio signal, resonance occur. So you can see both will be vibrate at the same frequency. Okay. Okay, so at this point, maximum energy from the radio wave is transferred to the circuit, allow the radio to clearly receive the broadcast. Okay, so this is another good application of resonance in our daily life. Okay, so now we have to take 5. Okay, so after take 5, we are going to discuss more questions related to subtopic today. Okay, so please stay tuned. Welcome back, everyone. Okay, so we have already finished our Learning Center 1 and Learning Center 2. So now we going to discuss the few questions which is related to subtopic of 5.2 today. So total, we are going to go through 5 questions. 3 questions objective and 2 questions will be example question or paper 2, section A. Okay, so you may share your answer in the chat room. Okay, so here diagram 24 shows a trolley attached to 2 identical springs. Okay, will be these 2. Okay, and vibrate horizontally. So that means that we go to the left and right. Okay, so if the experiment is repeated on the moon, so the frequency of the vibration of the spring will be increase, decrease, or remain unchanged, everyone. So this is a question. So what is the difference for the experiment conducted on Earth and on Moon? Okay, so the main difference here is actually the G, right? Okay, so the G different is it that cause the frequency different, natural frequency different. Okay, so here, so the frequency remains unchanged actually. So on the moon, because the spring vibrate horizontally, so the G is affected downward, right? Where towards the center of gravity. So now the experiment conducted horizontally. Okay, so that means that this will be not affected by G, so that the frequency will be remain unchanged. Besides that, this is actually example of the lotus spring. So the lotus spring frequency is affected by K and M actually. So K is stiffness of the spring, and then the M will be the mass. Okay, so that means that is independence to G. So we are sure that this is remain unchanged. So answer will be C. Okay, then the next question number 2. Okay, so diagram 20 shows a simple pendulum oscillating at its natural frequency. So again, the natural frequency here will be affected by G and L according to the formula we learned just now. Okay, so the angle of oscillation is theta. Okay, so the theta is actually referring to the amplitude of the oscillation system here. Okay, so the angle of oscillation is then increased. So example, we start with the experiment with 10 degree. So now we change the angle, the oscillation angle to example 15. So what will be going to change here? So first, amplitude, frequency, or period. Okay, just now I already told you, right? So the angle oscillation is actually represent the displacement. The displacement will consider the amplitude actually. Okay, you can see here. So when the angle oscillation increases, the displacement is increased. You can see from the figure I draw here. 10 degree will be here. 15 will be here. Okay, so hence the amplitude will be increased. So the answer is actually A. Okay, so for F and frequency and the period, just now we go through the formula already. So the frequency and the period is affected by G and L, right? It's not depends on the theta, the angle of oscillation here. So the answer is very clear. So it will be A. Okay, then now we go for question number 3. Okay, so the question number 3 is the question related to the button pendulum activity 5.9b in your textbook. Just now we go through together. Okay, so the question will be like this. Diagram 16 show a button pendulum. So pendulum Q, this is pushed to oscillate. So this is a driver lah, right? So this is a driver. or the external force will be carried out by this pendulum. This may cause other pendulum oscillate, if you still remember what we go through at the activity just now. Okay, so all P, R, S, and T pendulum will be oscillate. Okay, so pendulum S is found to oscillate the maximum amplitude. Okay, so you can see here. S will be oscillate maximum. Okay, as per mentioned just now, because the length of the S and Q is the same. So there, the natural frequency of S will be same as the frequency of the driver. So S will be achieve resonance and oscillate at the highest amplitude. Okay, so what is the option is correct? Okay, so the first, the natural frequency of Q is equal to the natural frequency of S. Is it correct? Just how we go through, right? So the S and Q have the same length. So the natural frequency for both pendulum will be the same. So seeing that the answer A is correct, okay, we look at the B. The mass of the pendulum Q is equal to S. Okay, so this one we not sure. But we know that for the simple pendulum, the natural frequency is depends on G, gravity, and L, length of the pendulum. Is not affected by the mass of the pendulum. So this one is actually not important. Out. Okay, then pendulum Q transfer force to pendulum S. Actually here is not. The energy transfer, not the force transfer. Okay, so here this is wrong already. Transfer energy. Okay, so D, pendulum Q transfer energy only to S. Wrong also, right? Because just now I tell you already. So the Q as a driver cause all the pendulum P, R, S, and T oscillate. So that means all of the pendulum here is receive the energy from the driver, which is Q here. Just the energy received by S is the highest because both of them have the same length, showing that they have the same natural frequency. So answer here is very clear, is A. Okay, so you look at the tips. Just now I go through with you already. Resonance occur when a system is forced to oscillate at an equivalent frequency to its natural frequency. So the system oscillate at the maximum amplitude. Okay, so this will be referring to A already. Okay, answer is A. Okay, so then now we go for question number 4. Is a paper 2 section A question. Okay, so diagram 2.1 show a loaded spring oscillating vertically. So that means up and down in water. The oscillating system experience damping. Okay, so what is damping? Just how we go through already. It's a oscillating system where the amplitude oscillate smaller and smaller with time. Okay, but the period or the frequency will be remain the same. Okay, so underline the correct answer in the bracket below. Okay, so damping is a situation where amplitude or wavelength of the oscillation decreases. Okay, so here just now we go through already. So it's very clear is amplitude. You can see A1, A2, A3 decreases. So answer is very clear, it's amplitude. Okay, it's amplitude. You can see these two amplitude. So it decreases with time. So answer is amplitude. Okay, then the next question. State one reason why damping occur in the oscillating system. Okay, if you still remember, we actually have two different type of damping, right? So one is internal damping, another one is external damping. External damping is loss of energy due to the energy loss used to overcome the friction. So another one is energy loss due to the compression or stretching of the particles in the system. Okay, so here you can give one of the answer. Okay, so the answer here is caused by energy loss due to friction or air resistance. See, this is considered the external damping. Okay, 1 mark, one answer enough already. Okay, then the C. So state the period of oscillating system. Okay, so the period oscillating system, just now I mentioned to you already. So you can just observe the first complete oscillating system, first oscillation. So you can see here, this will be 0.4. You can see the second one also the same. From 0.4 to 0.8, actually it's 0.4. Okay, so this is T1 and this is T2. Both is same. Okay, so here is 0.4 lah. Please give the correct unit together with your answer. Okay, then what is the frequency of the oscillating system? So frequency, we're using this formula, 1 over T. So that means it will be 1 over 0.4. Okay, so then you get your answer in 2.5 hertz. Okay, then question D. So what will happen to the period of the oscillating system when heavier load is used? Okay, so this is a loaded spring. So when weight increase with the same gravity, so the mass will be increased also. So the frequency of the, okay, so here the question asks about the period, right? So frequency and period, the difference here will be M and K reverse. Okay, so now question asks about period. So the relationship between the mass and the T is directly proportional. So when the M increase, the period will be increased, right? We can discuss by using this formula. So answer here will be increase I1. Okay, so this will be the answer. Okay, so now we go to our last question of today. Okay, so please go through together with me here. So diagram 4.1 shows 6 pendulum. We have J, K, L, M, N, and the driver here is very obvious to be X now. With different length being tied to a track. Okay, so pendulum X is oscillate at 2 hertz. So this is the driver. So the frequency is 2 hertz. Okay, so the others pendulum start to oscillate due to the oscillation of the pendulum X. Okay, so the X provide or transfer the energy to others pendulum here. Okay, so which pendulum will oscillate with the maximum amplitude? So for pendulum, we need to look at the length, right? Okay, so the length of the pendulum M is same with the length of X. So that means that we expected the maximum amplitude oscillate by pendulum M will be the maximum, will be the highest. So answer is M. So give the reason, just now we go through it. This is because the length of the pendulum N same as X. Or you can give the natural frequency for the M is same as the natural frequency of X now. Okay, you can see here. So the length of the N is equal to the length of the driver pendulum, which is X here. So the answer is very direct actually. For this subtopic, it's not very hard actually. Okay, then number 3, name the phenomenon. So this is the one and only phenomenon we learned today is at learning standard 1. So the phenomenon we know as resonance now. Okay, will be resonance. Okay, then now we go for C. Okay, so on diagram 4.2, sketch the displacement time graph to show the damping process. Okay, so for damping process, first the diagram are showing amplitude decreases with time. Second, the period will be unchanged, I1. So that means that we have to draw, this is a period. So 2 hertz, right? 2 hertz, F equal to 2, T will be 1 over 2 is 0.5. So you have to give 0.5 seconds. Here will be 1.0. Okay, so you have to give higher amplitude for the initial. Then after that, showing decreases of amplitude. Okay, so this will be the A1, this will be the A2. So you can see the time taken for first oscillation and second will be the same. So you have to give 0.1 and 0.5 and 1.0 here. Okay, and showing the amplitude decreases for your answer. Okay, so here will be the answer you want. Okay, but the time taken here must be changed. Here got mistake, everyone. So here, 0.5. Why? Because the frequency given 2 Hertz. Then the T will be 1/2, 0.5. So here will be 0.75, 1.0. This will be 1.25. This will be 1.5. 1.5, everyone. Okay, so you must give amplitude decreases for your answer and then show the same period for each oscillation. Okay, so that's all for my sharing today for subtopic of 5.2. Okay, so now I would like to share to you the link e-schedule. Okay, so please fill up the link within 30 minutes. Okay, you can using any email you are available. Okay, so to fill up the link so that you can get the kebangsaan e-schedule. Okay, so please remember to continue to support our Panitia Fizik Akademi Youtuber. Okay, so the class of Physics Form 5 Non-DLP group will be held on every Friday, 9:30 p.m. And for the DLP Form 4 class will be held on Sunday, 8:15 p.m. Okay, so thank you everyone for your support. Okay, so that's all for my sharing and see you again next time. Okay, so bye-bye everyone.
Penuh kesungguhan Akademi Youtuber Malaysia.